All right, thank you very much. So I'm Rob Bocchino from JPL, and I'm going to be talking about testing flight software modules with rules and scenarios. So the motivation for the talk is, of course, as we all know, unit testing is really critical. You want to make sure your modules work before you put them together and go into integration. So you're not faced with dealing with problems in integration that you could have caught in unit tests. So you really want to do as much unit testing as you can. The very sort of classical approach to this, it works, but it's very brute force. It says like, okay, we're just going to go through requirement by requirement, and then for every requirement, we'll write one or more tests completely by hand. Then we'll run some code coverage analysis, look at the results, add some more tests, and kind of just incrementally do this until we get to 100% coverage. Maybe we'll also look at things like branch coverage or cyclomatic complexity, but we just kind of like iterate this process until we think we have enough coverage. So this approach definitely works. It's tried and true, but there's some issues with it. So one issue is that it requires significant manual effort. So for example, it may be the case that in order to test some behavior, you have to get into a certain state and then do something. And getting into the state may involve a whole sequence of commands. And so in this kind of approach, you have to write that entire sequence manually. And then if you want to reuse the sequence in another test, you either have to write it all again or factor it into a function or do something like that. Another issue is that even with 100% code coverage, there may be many behaviors that you're not checking. So things like state and path coverage may be very incomplete, even though you have 100% code coverage. And with purely manual testing, it's often very hard to get good coverage of things like state coverage and path coverage. And a related issue is that without careful coding, your test can become unmaintainable, right? So it's very tempting. Let's say if you have a long sequence of commands you want to do for one test, let's say that help you've spent all the effort making that one test, and then you get to the next test and you're like, oh, okay, I actually need that sequence or maybe a subset of that sequence for this test. It's very tempting to just kind of copy paste. But if you start doing that, and especially if you do it over and over again, you can get to the point where the tests are really unmaintainable. A small change in expected behavior can cause lots of changes to kind of percolate through the system. And so we want to avoid that. Okay, so here's an alternative approach that we've been using at JPL in the group I work in, the small scale flight software group. So the idea is that you can organize your tests as scenarios that apply rules. So what do I mean by that? Well, so first of all, a rule is a simple reusable test behavior that has two parts. So there's a precondition, which is a predicate function that basically says for any state S, does it make sense to apply this rule in that state? And I'll show some examples that will clarify what this means, but that's the basic idea. It's a predicate on state. And then there's an action which will typically call the interface under test and check the result. So an example could be issue a command and check for expected telemetry. And then once you have some rules, you can put them together into scenarios. So a scenario is a recipe for using rules to construct tests. So some examples are a fixed sequence of rules. You could have a random picker that randomly picks rules and sort of constructs random sequences. You could have a pre-programmed simulation. So for example, you could put the rules together in such a way that you're simulating a duty cycle, turn something on, do some work, turn it off, repeat. You could have a composition of scenarios. So you can have two different scenarios and then make another scenario by interleaving them. Or you could have a scenario that says, on some condition, do this scenario or that scenario. Or you could have a loop or just sort of standard programming constructs. So you can compose scenarios that way. So here's a simple example to kind of clarify the idea. So imagine we have a buffer manager, which is a component that just on request provides some memory buffers. So we could have a rule allocate OK. Its precondition is there must be a buffer available. And the action is request a buffer and then check that the expected result happens, namely that we actually got a buffer because we're in a state where we expect to get a buffer. So the precondition says we're in that state and the action says, okay, when we request one, this is what should happen. And then similarly, we could have deallocate OK. So that one wouldn't make sense to apply in a state where there's no allocation, right? Because deallocation only makes sense if something's allocated. So the precondition is we have at least one buffer allocated, and the action is deallocate and check that it worked. And then a third one might be no buffers available. So the precondition is there are no buffers available, i.e. all buffers are allocated. and the action is request a buffer. And in this case, check that we get the failure and we get the expected error, the event report or whatever it is indicating the error. So it's sort of a controlled way to apply different actions in different states where the result you expect to get from the action will depend on what state you're in. And then so here are some examples of scenarios. So here are some really simple sequence scenarios. So these are useful for doing kind of initial testing of rules. So a scenario allocate OK would be very simple. It's just, OK, in the initial state where we assume no buffers are allocated, just apply it. And that works because the precondition is no buffers allocated. So the precondition is satisfied. We can just apply the rule. And then the second column is deallocate OK test. So in that one, notice that we can't just apply the rule deallocate OK in the initial state because nothing's allocated. So a minimal test here is apply the rule allocate OK to get into the state where one thing's allocated, and then apply deallocate OK to deallocate it. And as it says at the bottom, the apply operation is going to check the precondition and run the action. So if in the second case we apply the deallocate OK without applying the first allocate OK, we would actually get a test error. So there would be a test assertion that would fail, and it would say, hey, you're trying to apply a deallocate rule in a state where the precondition isn't satisfied because nothing's allocated. And then the third example is no buffers test. So in that one, we just have to apply the rule allocate OK enough times to consume all the allocations so nothing's available, and then we apply the rule allocate no buffers available. And again, at every step, the precondition has to be satisfied in order for the test to succeed. Here's an example of a random scenario. So we apply no allocations and then OK and so forth. And if you go through this, you can kind of convince yourself that at every step, it actually makes sense to apply the rule based on the state you're in. So there's basically a random selector here that at every step in the process will pick a random rule, but will filter the picking on satisfaction of the precondition. So only pick a rule if its precondition is true. And this is very useful for constructing scenarios of really arbitrary length. So you can run this as long as you want. You can do thousands, millions of rule applications. And we found a lot of tricky bugs this way through this kind of random testing. So here are some benefits of the approach. So we found that if you do this, you get very well-structured tests. So the rules and scenarios sort of force you into a pattern that is easy to follow, and if you follow it, you get structure. And so in particular, the pattern is going to ward off bad coding practices like the copy-paste of a long sequence of commands that I mentioned at the beginning, so you avoid that. And the tests are very modular because they're all sort of constructed from rules and compositions of rules and scenarios, so they're very easy to understand and maintain. In terms of test quality, it's good because the rules actually allow you to model the system external to the module under test. So we found that this is very important in unit testing, right? So a lot of what you need to do for good unit testing is figure out, okay, there's this code I want to test. And when I plug it into a real system, the real system is going to be doing all these things. So in order to have a good test of that module, I really need to figure out how to abstract the behavior of the external system and represent it to the level of detail that's needed for the test. And the rules help you do that. And as I mentioned before, you can automatically generate tests from these scenarios. So a scenario is really a recipe for using rules to construct tests. And then they can be parameterized, for example, on how long you want to run a random scenario. And then by doing that, you can apply many, many rules and thereby cover many more behaviors than you could with manual testing. And you can also do things like using model checkers or fuzz testers to pick the rules. So mostly we've used the random testing because it's simple, but we've experimented a little bit with using the spin model checker to do the rule picking, and that also works. Okay, so now I'd like to move on and talk about S-Test, which is an open source C++ framework that we've released that implements this idea. So in this framework, a rule is implemented as a class template. So the state type is a template parameter, and the precondition and action are pure virtual functions.